We're going to go through a quick review of the derivatives of the trig functions that we know, and then we'll develop the derivatives of the inverse trig functions, the 4 inverse trig functions that we're going to work with on the AP test. So we remember that the derivative of the sine function was positive cosine, the derivative of cosine was negative sine, the derivative of tangent was secant squared, and the derivative of secant was secant tangent. We don't need to know these. We don't have to readily have them in between our ears, because if we're asked for the derivative of cosecant, we can just as easily find the derivative of 1 over sine using the quotient rule. Here we can find the derivative of cosine over sine using the quotient rule. So it's not that we'll never see these, it's just that we have an alternate way to develop them. We can actually derive them and then take the derivative of that result, and it will be equivalent. Now again, this is actually what you need to know. When we have composed functions where some expression in x has been put into the sine function machine, we're going to have to use the chain rule to find these derivatives. So here is actually what you need to know. Here are the rules that need to be in your notes. They're the same, except it is the derivative of the outside, not changing the inside, times the derivative of what's inside on all 4 of those that we need to know. So you already have these in prior notes. This is just a review. So make sure, because we are going to see these and need to know these, make sure you can do that. Now I want to actually take the time to step by step go through how we're going to find the derivative of the sine inverse function, but I'm only going to do it for sine inverse because it's the same kind of idea for the other inverse functions that we're going to be taking the derivative of. So this is basically, when it boils down to it, you're going to have formulas that you're going to have to memorize, and there's really no other way around it, because we're in a time testing situation. You're not going to have time to derive these using implicit differentiation every time you need it. So it's my suggestion that when we get down to the actual formulas of the inverse trig functions, after we kind of sort of develop this one, that you just make flashcards and you just memorize those, because it's just going to help us in a time situation. So based on our last lesson, we know that if y equals the sine inverse of x, then it has to be true that the sine of y equals x. And this is why we're going to use implicit differentiation to start to develop the derivative of sine inverse. If I implicitly differentiate this with respect to x, it's the derivative of the outside, which I know is cosine, not changing the inside, times the derivative of what's inside with respect to x. So there's the derivative of this side of the equal sign, and that has to equal the derivative of x with respect to x, which is 1. So in implicit differentiation, we just differentiate term by term, and then we solve for dy dx. So I'm going to divide both sides by cosine of y. All right, so I need dy dx in terms of x, not in terms of y. So we're going to develop how we could actually give this whole expression as an expression in x. So here's what we're going to do. We're going to go back to the Pythagorean identity. Here our angle measure is y. And we have to remember that the sine squared of an angle measure plus the cosine squared of that same angle measure equals 1. I'm going to solve this for the cosine squared of y, which means I'm subtracting sine squared of y from both sides. I'm taking the square root of both sides, which means I have a positive root and a negative root. I need to determine where in the plane that I am. Is it the positive root? Is it the negative root? So on this interval, cosine is positive. Cosine's positive on the interval from pi over 2 to positive pi over 2. Cosine is positive. So look at the graph of the parent cosine function and you'll see that I'm right about that. That's, you know, a great big hill. That's the top part of the cosine function. So we're after the positive root. So it has to be true that the cosine of y is 1 minus sine of y squared. So let's get that written down. I just wanted you to see where all of this came from so you will understand what's going on here. And now if you'll remember, We started with y equals the sine inverse of x, and so we said it had to be true that x must equal the sine of y. And that's why I'm telling you that the cosine of y equals the square root of 1 minus x squared. So I'm going to substitute this in for the cosine of y, and that's how I wind up here. The derivative of y with respect to x is 1 over the square root of 1 minus x squared. So as I said, we developed that. Clearly you see all of the trig relationships that are there. We even went back to the Pythagorean identity here to get our derivative in terms of the independent variable, but we just don't have time, plus it's quite trig intensive to try to make sure that we get where we need to be. So here are the formulas that you need. The ones here in red are the 3 that you're responsible for. So yes, we could use the same technique with tangent inverse and secant inverse, but it's just too time intensive. So you are responsible for these 3 derivative formulas, and I'm giving them to you in the chain rule form. If we incorporate the chain rule, this is the form that they will take. So instead of having x, u is some expression in x. So we're going to need the chain rule. If we have the function, the sine inverse of u over a, where a is a constant, a is some constant. For us a while ago, the expression u was x, and the constant was 1. So we wound up with 1 over the square root of the quantity 1 minus x squared. But just in case that's not the case, then the chain rule form is 1 over the square root of your constant squared minus your expression in x squared. That's the derivative of the outside not changing the inside, and then times the derivative of what's inside. So we developed that one so you can kind of see all the pieces there. Tangent inverse of u over a is 1 over your constant squared, which is the same thing. It's the denominator here of this expression. It's your constant squared plus your expression in x squared. There's the derivative of the outside not changing the inside times the derivative of what's inside. And the derivative of secant inverse of u over a is 1 over the absolute value of the expression in x times the square root of, now it's the expression in x squared minus the constant squared. So this relationship is reversed under the root sign. But what's most important, what we look for secant inverse, is that down here in the denominator we have this expression in x on the outside of the root. So that's what we're going to look for if we think it's secant inverse, okay? And then here is sine inverse and tan inverse. Now notice I did not tell you that you need to know cosine inverse, because it turns out that cosine inverse doesn't really show up on the test that much. And if it did, it's just the opposite of the sine inverse derivative. And we don't ever see cotangent inverse or cosecant inverse. So these 3 are the ones that I want in between your ears. You're responsible, starting the next time you come to class, when we're going to do homework, you're responsible for knowing those 3 derivatives. That's non-negotiable, so make sure they're in between your ears. Flashcards are a wonderful idea at this point. If you're still not sold on them yet, maybe this lesson will sell them. Okay. So find the derivative of y equals the cosine inverse of 5x. Okay, well you said they never asked for cosine inverse. Well, if they do, all you need to put in between your ears is that it is the sine inverse with a negative on it. That's all it is. We need to recognize u, and we need to recognize a. Those are the 2 things that I would have you do anytime that you're asked for the trig of an inverse function. We know that sine inverse, which is the opposite of the sine inverse, so that is 1 over the square root of a squared minus u quantity squared. There's the derivative of the outside, not changing the inside, times the derivative of what's inside. And this is the inside that I'm talking about. All right? So fairly easy to do if you've just got those things in your head. All right, so u is 1 minus x squared. A here is again 1. How do I know it's 1? Well, because there's not a fraction. And if there's not a fraction, I can always write it as over 1. It might be a good idea here too, if you wanted to go ahead and write down what du dx is. So you can just add that right in. So dy dx equals the derivative of the outside, which is this, right? Here is a, here is u, times the whole thing times, not just in the denominator, but the whole thing times the derivative of what's inside. So we could clean this up. You don't have to, but understand that it would look like 1 minus the quantity 1 minus x squared squared. So not difficult. Find the derivative of y equals the quantity x plus 1 times sine inverse of 4x. So we may not just encounter these alone. They may be buried up in a product rule or a quotient rule or maybe even another chain rule. So look for that as well. So dy dx here is going to be a product rule. And that product rule is 1 d2. Now here u is 4x, a is 1, and du dx is 4. So it's 1 over the square root of the quantity a squared, which is 1, minus the quantity x, or u, sorry, squared, times the derivative of what's inside. So there's 1 d2 plus 2, which is just the sine inverse of 4x. Make good use of parentheses. This is a product here. d1. All right? And I think we can get to this final one before the end of the video. So I think we're going to get this all done in one video. So here it says find the derivative of x plus y equals the tan inverse of the quantity x squared plus 3y. So now we have a implicit differentiation, and we're differentiating with respect to x. So we have 1 plus dy dx, there's the derivative of the left-hand side. The derivative of tan inverse is 1 over a squared, and a is 1, so that's 1, plus u squared, right? Not changing what's inside. Now, times the derivative of what's inside. So now I'm just taking the derivative of this with respect to x. So that's 2x plus 3, the derivative of y with respect to x, is dy dx. Now, the next step is to solve for dy dx. I'm going to try to do this really quickly. I want everything with dy dx on the left-hand side. So this distributes out over here. I have 3 dy dx times this, so I'm going to subtract that. That's 3 over 1 plus this quantity times dy dx equals, I'm going to move this negative, this 1 over here by negative, and I still have over here a 2x over the quantity 1 plus x squared plus 3y quantity squared. I am running out of time, but I would factor out dy dx and then divide both sides by what's left. I'm not going to have another 30-second video. So we're done. Come to class next time and we'll do some homework problems.